Hey yo hey! I hope you had fun in the previous session where we learned the volume and capacity of spheres using a cone. Did you try it yourself? No? Hey, you really must, because these are simple experiments, and as soon as you have performed them and seen that they really work, I can assure you that you will never be able to forget the concepts. And when that happens, you will be unrestrained in applying those concepts to solve problems of all types. Talking about solving problems, we haven't really solved many problems based on the volume and capacity of spheres, right? So let's take this video to do just that. We'll be solving some really interesting problems based on the volume and capacity of spheres as well as hemispheres. So, ready for the challenges that lie ahead? Let's roll. Now, before we delve right into solving the problems, it's always better to recapitulate the important formulae that may come in handy. We know that for a sphere of radius r, its volume or capacity is calculated using 4 by 3 pi r cubed. And for a hemisphere of base radius r, its volume would of course be half of that of the sphere, which is the same as 2 by 3 pi r cubed. Now, it's pretty evident that in each of these formulae, the only prerequisite is the radius. So, it's rare that you would get a direct question based on the volume of these shapes. It would be too easy for you. More often than not, you would get an indirect application of these formulas. Nothing to worry about though. You have solved ample questions in this chapter, and I am confident that you will be able to solve the upcoming ones rather easily. So, prepare yourself. It's time to tackle the questions. So, here's the first question. It states that the largest possible sphere is carved out of a cube of side 7 centimeters, and we have to find the volume of the sphere. That's it. Yeah, that's it. Sounds pretty simple, right? It's actually really simple if you understand the concept. There's a cube of size 7 centimeters and a sphere is carved out of this cube. Not just any sphere though. It's the largest possible sphere that could have been carved out of the cube. And all we need to do is find the volume of this sphere. Now, to find the volume of this sphere, we need to know its radius. And we can also manage if we get to know its diameter. So, what do you think would be the diameter of this sphere? Isn't it intuitive? Since it's the largest possible sphere, its diameter would be the same as the length of the side or edge of the cube, which is 7 centimeters. Any more than 7 centimeters would mean that the sphere is going beyond the cube, which is not possible because we are carving it. And any less than 7 centimeters would mean that the sphere is not the largest. So, now that the diameter is 7 centimeters, the radius would of course be 7 by 2 centimeters. Then, on substituting this value in the formula, we get the volume of the sphere is equal to 4 by 3 pi into 7 by 2 whole cube. Now, on using pi is equal to 22 by 7 and simplifying, we get the volume of the sphere is equal to 179.67 cubic centimeters. And that, my friend, is your answer. Moving on to the next question. This one states that a solid sphere of radius 1 centimeter is melted and stretched into a wire of length 100 centimeters. And we have to find the radius of the wire. How difficult is that? Not at all. All we need is some visualization. There's a solid sphere of radius, say Rs, is equal to 1 centimeter. And this solid sphere is melted and stretched to form a wire of length 100 centimeters. Now, we need to find the radius of this wire, for which we first need to decide the shape of the wire. It's a cylinder, right? If you look closely, you will be able to see that it's a closed solid with two parallel circular bases connected by this curved surface. it indeed is a cylinder with height, say hc, is equal to 100 centimeters. In questions like this one, unless mentioned otherwise, you can safely assume that a wire is cylindrical in shape. Anyway, coming back to our question, we essentially need to find the volume of the sphere using the given radius. Then equate that volume to the volume of the cylinder in this formula. Substitute the given value of hc and find the value of rc, which is nothing but the radius of the wire. See, the question is practically solved. Let's get over with the calculations in a jiffy. Now, the radius of the sphere is given as 1 centimeter. So, its volume would just be 4 by 3 into 22 by 7 into 1 centimeter whole cube, which on simplification gives us 88 by 21 cubic centimeters. Now, we have already discussed that this volume would be the same as the volume of the cylindrical wire. So, pi rc squared into hc is equal to 88 by 21 cubic centimeters. On substituting the value of hc as 100 centimeters and pi as the usual 22 by 7, we get 22 by 7 into rc squared into 100 centimeters is equal to 88 by 21 cubic centimeters. On simplifying this, we get rc squared is equal to 88 by 21 into 7 by 22 into 1 by 100, which is the same as 1 by 75. So, rc is equal to root over 1 by 75, which would give us 1 by 5 root 3. On rationalizing the denominator, we get rc is equal to root 3 by 15, which is the same as 0.12 centimeters. Thus, rc is equal to 0.12 centimeters. So basically, the 100 centimeter long cylindrical wire, which was formed by melting the solid cube of radius 1 centimeter, has a radius of 0.12 centimeters. Hey, we solved 2 questions in just around 5 minutes. Not bad at all. Let us now look at something that deals with hemispheres. Say this one. It states that a hemispherical tank is made up of an iron sheet 1 centimeter thick. The inner radius is 1 meter, and we just have to find the volume of iron used to make the tank. This one's as easy as the previous ones. There's a hemispherical tank made up of an iron sheet 1 centimeter thick. The inner radius, which is basically this part, is given as 1 meter. And all we have to do is find the volume of iron used in making the tank. Pretty simple, isn't it? Hold on. There's a catch here. The question asks us to find the volume of the iron used, not the volume of the complete hemispherical tank. So basically, we have to find the volume of just this part, not that of the complete hemisphere. We can do that. We have done it before. Here, we just have to find the volume of the complete hemisphere. Then, subtract the volume of the smaller hemisphere from it, and voila, we would get the volume of the iron used. Makes sense, right? Let's give it a shot. So, as per the question, the inner radius or the radius of the inner hemisphere, say Ri, is 1 meter. And since the thickness is given as 1 centimeter, the outer radius, say Ro, would just be the sum of the inner radius and the thickness, that is 1 meter plus 1 centimeter, or 1 meter plus 0.01 meter, which is the same as 1.01 meters. Now, the volume of the iron used, as we just discussed, would be the volume of the outer hemisphere minus the volume of the inner hemisphere, that is 2 by 3 pi Ro cubed minus 2 by 3 pi Ri cubed. On taking 2 by 3 pi common and then substituting the values of the given radii, we get 2 by 3 into 22 by 7 into 1.01 whole cubed minus 1 cubed. On multiple levels of simplification, we finally arrive at the volume of the iron is equal to 0.06349 cubic meters. So basically, the volume of iron used in making this hemispherical tank is 0.06349 cubic meters. Hey, we are at the end of this video already. I hope you enjoyed solving problems based on the volume of spheres and hemispheres. Well, frankly, you haven't even solved a handful. You really need much more practice to be a true master in this concept. That's exactly why we have created the quiz section only for you. So, if it pleases you, watch this video once again for a greater understanding and then use the learnings to solve problems in the quiz section. I'll be seeing you super soon with another amazing video. Till then, keep revising and keep practicing.